Hello and welcome to Lecture 15. Today we'll pick up where we left off talking about pollution, this time specifically focusing on what technologies we put in automobiles and trucks to uh, reduce the amount of pollution and other technologies we use to prevent the pollutants from forming. So earlier we had introduced equilibrium and we had demonstrated how at the flame temperature that the combustion is occurring, there's a significant amount of dissociation of carbon dioxide into carbon monoxide. And at that temperature, when there is a number of free radicals of oxygen, you're actually also going to get some uh, nitric oxide formation uh, within the engine compartment. Now, at the temperature that we typically exhaust the gases out of the tailpipe, there's practically zero nitric oxide and carbon monoxide at equilibrium. Um, but at the flame temperature, there's a significant amount. So how do we bring these products to complete combustion to equilibrium at the lower temperature where they wouldn't exist? Number of ways we do that. The primary method is with a catalytic converter in gasoline cars and an SCR for diesel vehicles. This chart, we've talked about some of the species, some of these first few species that exist in the exhaust products, and at the flame temperature, they're on the order of tenths of a percent, 0.2 to 0.4% here for some of these more exotic species. When we get down to 700 degrees, we're talking basically zero, e to the negative 19. So parts per trillion at this level. There are some more heavier things that do exist at adiabatic flame temperature, and they also disappear at lower temperatures, but these are sometimes a little harder to shift to equilibrium because they're heavier molecules and have greater activation energy in their equilibrium reactions. So basically, with these larger molecules, they may exist in lower concentrations at the adiabatic flame temperature, but they freeze at a higher temperature because their activation barrier is higher. So some of these species, like carbon monoxide, where there might be almost 1% carbon monoxide, it may not freeze until 1500 degrees. So it shows up in the tail products again on the part per million basis, because at 1500 degrees there's still enough energy in that gas to overcome the activation energy. That is not the case necessarily for some of these heavier ammonia, um, formaldehyde, other heavier molecules down here that would freeze right at the moment that they're formed. So what do we typically do in combustion? We break the fuel down into carbon monoxide and hydrogen. That happens instantly as it's heated up and it decomposes and starts to react. The reaction of hydrogen itself burning is quite fast and on orders of magnitude faster than the final burning phase of carbon monoxide to carbon dioxide. So in the intermediate there's a lot of radicals, the hydroxyl radicals, free hydrogen, free oxygen, and that's what ends up producing these other species that we don't want in our exhaust products. So if we focus on carbon monoxide, it's definitely going to form in rich mixtures. When there's not enough oxygen to burn everything to CO2, there's a significant amount of CO. But interestingly, it actually forms under some cases that there's more CO in slightly lean combustion than slightly rich combustion, just due to some of the other equilibrium reactions that are occurring and the flame temperature itself. So let's talk about how we would operate the engine in order to have more complete combustion. We'd want to run leaner, but that's also going to reduce power in the engine. If we run leaner and by recirculating exhaust, we can still get to the same high temperature. So when we do that, we can maintain efficiency while running leaner, and that should drive down carbon monoxide. I'm not going to focus on these terms here, but they're generally different control methods in how you operate the engine to reduce carbon monoxide. And the biggest impact is as you throttle the engine. You're getting less CO, but on a per power output of the engine, you're actually getting more CO at a low power ratio, which is the opposite of what we want. The unburned hydrocarbons, slightly different than the carbon monoxide. The majority of the unburned hydrocarbons come from the areas in the corners of the engine along the wall where the flame gets quenched. They're more products of incomplete combustion than of the equilibrium type reactions the way carbon monoxide is. The unburned hydrocarbons can come from the fuel. They can also come from all the different oils that we use to lubricate the engines. There's also unburned hydrocarbons emitted into the air directly from the fuel tank and from filling stations. So a lot of states have adopted, if you fill up in California and you have this big clunky seeming fuel nozzle that you're putting in your gas tank, there's actually a device in there that's sucking the fuel vapors and making sure that those are pulled back into the filling station rather than venting to the atmosphere. Introducing NOx at production. I showed this graph before. It's very similar to the flame temperature, just like flame speed. There's a very strong correlation of nitric oxide production to what the flame temperature is. There's a significant activation energy to forming nitric oxide because the N2 molecule has to break, and a nitrogen molecule has 3 bonds. So if you want to break a N2 molecule, you're breaking 3 bonds, and that takes a significant amount of energy. So it's really at high flame temperatures where there's significant NO production. Now it's not purely an equilibrium reaction. It happens in 2 steps, and what this leads to is really 2 ways that NO forms. There's the Zeldovich mechanism, which is a 2-step process where there's a free radical oxygen that is bouncing around from some other part of the combustion, and that breaks apart a nitrogen molecule. This is really slow, again, because there's 3 bonds in that nitrogen molecule, and that's hard to break apart. As soon as you've broken that apart and made one nitric oxide and a free radical nitrogen, almost instantly that nitrogen is going to be oxidized with an oxygen atom. And the result of that is a second molecule of nitric oxide and a new oxygen free radical that can go back and participate in the first reaction. The first reaction here is the limiting one because of breaking that triple bond. The second one can essentially be instantaneous after the first happens. So if we were to look just at the Zeldovich mechanism, given some amount of time at some flame temperature, that the kinetics of that reaction are going to follow some curve where initially a lot of NO is going to be produced, and then it's going to reach closer and closer to its equilibrium concentration after some infinite amount of time. So to characterize how quickly it starts out, we give it something, a characteristic time, this tau NO, and it's the if you took the slope of nitric oxide formation at any given moment and figured out how long at that rate it would take to reach equilibrium, that gives us a time constant that we can characterize the combustion by. So a single number, since it's infinity for everything to truly reach equilibrium, this gives us some way to tell us how fast we're headed towards equilibrium. There's actually a second mechanism that occurs within the flame itself, and we call that the prompt NO formation. So as initially when they started to reduce NO formation in engines, the Zeldovich mechanism was known, and they put in controls in the engine to speed things up and not give the reaction enough time to happen. When they got really good at mitigating NO production, and that's what we called thermal NOx production with the Zeldovich mechanism, they realized that the best they could do wasn't going to zero. And there must have been something else that was forming nitric oxide. So this is what we consider prompt NO, because it happens essentially instantaneously within the flame itself. So coming back to the Clean Air Act, in 1970 they passed some amendments, and this was the first real regulation of, okay, what are the standards that we're going to hold the engine manufacturers to? And the standard was they wanted a 90% reduction in the exhaust of unburned hydrocarbons, carbon monoxide, and oxides of nitrogen from a baseline of pre-1970. So the way they needed to do that is they had to oxidize carbon monoxide to CO2. They had to oxidize whatever unburned hydrocarbon there was all the way to CO2 and water. And then to get rid of the NOx, they have to go the other way. They have to reduce it. It's a reducing reaction. So generally in chemistry, you either have oxidizing environments or reducing environments. If there's a plethora of oxygen, it's an oxidizing environment. If it's the other way and you have to reduce it, they compete against each other. It's like acid and base. So how do we get all three of these things to happen simultaneously? Well, that was the magic behind a three-way catalyst. It does all three of those things simultaneously. And this technology was originally developed in 1975 by Ford and a company that's no longer around, Engelhard, as well as Bosch and Volvo were involved in partners on this project. And it is a ceramic honeycomb that they put catalyst on there, typically platinum, and it is able to both oxidize the CO and hydrocarbon and reduce the NO, but it's only able, if you focus on this chart here, it's only able to convert, they wanted to convert 90%. It's only able to do that in a very small region right around stoichiometric. Okay, so that works for a gasoline engine, which can always operate at stoichiometric because you're putting in this charge of fuel and air. It's not going to work for your diesel engines. So we'll come back to a different technology that works for the diesel engines. The biggest problem with this catalytic converter was that it was very quickly poisoned by lead. In very trace amounts, within a matter of hours, these reactions would shut down and you would basically kill the catalytic converter. So this was the motivation to finally, they'd known lead was bad for a long time, this was the motivation to finally get lead out of the fuel. And that was when we had to come up with different anti-knock agents, starting with MMT, moving to MBTE, and then finally to ethanol. There is another way to minimize the NO and CO formation, and that was to use exhaust gas recirculation to get to the high temperatures where we wanted to burn things and things go to equilibrium, but run at a lower flame temperature. So we're still stoichiometric, but we've lowered the flame temperature because you've diluted it with products. So that was a approach taken by the Japanese. I thought I had that on this slide. When Ford and GM and others started adopting the three-way catalyst, the Japanese auto manufacturers used exhaust gas recirculation and pumped that back into the engine. And they were able to meet the first generation standards that way while still using the leaded fuel. And at the time, leaded fuel was significantly cheaper. And this event, when Ford and GM and others switched to catalytic converters, this was one of the moments in history that allowed the Japanese auto manufacturers to really gain a foothold in the American market. And it was their initial choice to use exhaust gas recirculation rather than a catalytic converter. So if we need to, coming back to this chart on how the catalytic converter oxidizes the CO and the hydrocarbons while reducing the NO, it works in this very small band, and before we had shown how much variability there was in the air to fuel ratio between cylinders, how do we ensure that what the catalytic converter sees is in this very small ratio? Now the catalytic converter is downstream in the exhaust system where several cylinder charges have all mixed, so there's some averaging effect by the time it's seen, but we still need to precisely control the air to fuel ratio. And that's done with a control system such as this. It starts with, you have a throttle here that is throttling the engine, so deciding how much power you want out of the engine. And while that is controlling the airflow, we need a hot wire airflow meter to measure what that flow is. So we can very easily measure the position of our throttle valve, but it's a little harder to measure the mass flow. So this introduces significant error, but that goes to the brains of our car, our ECU. And then we need to measure what the oxygen was in the exhaust. So if we know we want to burn it stoichiometric, there should be essentially 0 oxygen left in the exhaust. And then finally, we're going to measure the temperature of things in our cylinder. All of that goes to the brains of our ECU, and what we send out is a control signal that tells us exactly how much fuel to inject. So as part of the introducing the catalytic converter, that was the same time that we finally started moving to, on a widespread scale, using electronic control units and fuel injection rather than carbureted engines. They go hand in hand, they help each other. The catalytic converter would not function at its best in a carbureted engine. We need this additional control of the air to fuel ratio. So I mentioned this oxygen sensor I showed you that's measuring in what the oxygen is of the products. What exactly is that? Well, it's actually a solid oxide fuel cell, which is the technology I do my research on. And a solid oxide fuel cell is a pretty interesting device. It is a ceramic that allows oxygen ions, O2 negatives, to pass through, but it does not, so those are okay, but electrons cannot go through. And so by measuring the potential and how many oxygen atoms go through this sensor, we measure the voltage by these electrons that cannot go through the membrane. And what we get when we plot the voltage of this sensor as a function of the air to fuel ratio, we get this shape. Kind of looks like a lambda. the Greek letter lambda. So we called it a lambda sensor. You can see how it drops off very suddenly right at an air to fuel ratio of 1. And this is what we're trying to measure. We want to be somewhere in this region, and because it's so steep right around an air to fuel ratio of 1, we can actually quite precisely measure what the air to fuel ratio was, and that allows us to control the fuel injector. So if I were to put that lambda sensor upstream of the catalytic converter, I'm going to see the individual charges of the cylinders as the air pulses through. If I then put that same sensor after the catalytic converter is going to flatten that out quite a bit, because if there's more oxygen than we'd like, that means the fuel hasn't burned completely, so the catalytic converter is going to oxidize that the unburned carbon monoxide. And if there's a shortage of oxygen, it's going to be a reducing environment, and that is going to reduce the nitric oxide. So after the catalytic converter, we get a very steady reading from our lambda sensor. So that Air Quality Act update in 1970, everyone agreed to a 90% reduction. It was being phased in, so it was formally going into effect in 1977. The catalytic converter was finally commercialized in 1975, so they just came in just in the nick of time. And it exceeded the expectations. You were able to get a 95 to 99% reduction compared to the baselines. So GM, as soon as the technology was available, they put it on every model they had immediately. Ford rolled it out in phases, started with about half of their models having catalytic converters so that folks could have an option to choose between a leaded gasoline vehicle and an unleaded gasoline vehicle, putting it in the consumer choice. After they looked at it for 6 months, they went fully 100% as well, and the Japanese did not. This had a huge impact on what the emissions were. If you looked at what they were in I think this chart is showing us I think that, this is right. This is the regulated standard, and in 1976 they were able to be well under that standard in hydrocarbons, carbon monoxide, and NOx, in some cases by an order of magnitude. Now initially in 1977 the standard was 1.5. I believe that's milligrams per liter, or per meter cubed. That is now down around the area of 0.07. So we've come a long ways in the standards for NOx in particular. Diesel systems, since they are not running at stoichiometric, they cannot do both the oxidation and reducing at the exact same time. So it is a two-phase system that they use in most diesel vehicles that use exhaust gas cleanup. They start with a oxidation catalyst, and that is going to get rid of your CO, and it's going to take some of the NO to NO2, and your unburned hydrocarbons are going to react and form water and CO2 as well. The second phase, now this was the more recent addition, and this is the more complex portion of a diesel exhaust gas cleanup, and it's called selective catalytic reduction. So we don't want to reduce everything. If we reduce everything, we're going to turn the water and CO2 back into hydrocarbons and CO. We don't want to do that. We want to specifically target the NO2 and try and get that back, and any we want to try and get that back to nitrogen and oxygen. And the way we're going to do that is by injecting ammonia. And that way the ammonia nitrogen is going to pair up with the nitric oxide nitrogen, because the oxygen and the hydrogen want to get together and make water. So the reaction's listed for you here. You have nitric oxide that was formed in the engine itself and in the oxidation catalyst. We're going to spray in ammonia, and that's going to form nitrogen and water. So what is this fluid? Well, it's mostly ammonia. It's diluted. It's generally called diesel exhaust fluid. If you see it on the shelves at a service station, it's called diesel exhaust fluid. What it actually is chemically is urea. Urea has a bad connotation. It's, sounds like urine. It's pretty close to what urine is. So they went for a little bit of branding, and they call it diesel exhaust fluid. It's on Mercedes as Blue Tech. BMW had a system. Volvo clearly had a system that could work, but they opted for a cheaper system, and that was the big scandal with the diesel Volkswagens. As of yet, the Mercedes and BMWs have continued to show that they were able to achieve the mandated reductions. Their SCR was apparently performing better than the Volkswagens. So we have these standards. How do we test the vehicles for the standards? Do we leave it up to the manufacturers the way the EU does, or do we independently test and verify with our own standards? So example of the EU test is a very different drive cycle. So it's steady acceleration to 15 or 18 kilometers an hour, shut the engine down. Accelerate to 35 kilometers an hour, come to a stop. Accelerate up to 50 kilometers an hour, slow down a little bit, and then stop. Fairly easy drive cycle for the EU test. The American test is something closer to how you would actually operate as you leave your house, get on the freeway, go quite fast for a bit, get off the freeway, stop and start city traffic, cruising through city traffic. Maybe you made a few lights, some more stoplights, and then on the way home you get back on the freeway and you have a high-speed region. These tests are a bit more difficult to control emissions on. So the US tests have for years been stringent. The EU has begun to adopt stricter drive cycle tests, but they're not fully implemented, and most of the time they allow the auto manufacturers to outsource it to private companies that do the testing. And those private companies are motivated to provide their customers with the best score possible, so they pull a lot of tricks, testing on certain weather days that help with emissions, doing all sorts of things to reduce the drag on the vehicle so the engine doesn't have to work as hard to meet this speed cycle. Lots of tricks they play to improve their score on EU tests that we generally don't allow in US testing, because they're sent to an independent agency that does the testing. So let's talk about emissions at hot and cold start. The catalytic converter, I mentioned this in previous lectures, takes some time to warm up, and its percent at reducing, oxidizing the carbon monoxide and hydrocarbons increases as a function of temperature. So at around 300 degrees is where we consider the catalytic converter warmed up, ready to go. And smart controls, if you have one of these new cars that stops, like a hybrid that's able to stop and start on its own, you might find that when you first start it up on a cold day, it continues running for a while, and then it drops down into some operation where it's doing your battery driving and then turning the engine on and off occasionally. And the reason for that is it wants to heat up the hydrocarbon or sorry, it wants to heat up the catalytic converter uh, first, and then it'll keep it warm just by using the engine intermittently. So a question that comes up fairly often is, since the majority of our emissions on a typical, 20-minute drive to work are occurring in the first 2 or 3 minutes of that drive when the engine's cold, when you come to a stop sign, is it better for the engine to idle or restart? Initially, I would have answered that it is better to idle. Once that engine is warm, it is quite clean when you're idling the engine. Now they've gotten better at reactivating that catalytic converter, keeping it warm by adding insulation. I mean, it used to just be inside the exhaust pipe, no insulation around it whatsoever. Now they're really considering that in part of the design of the vehicles, and that is why a lot of the hybrids have moved to this shut the engine down while you're at a stoplight to reduce emissions. I want to come back to the diesel cycles, and coming back to the health impacts. This is the chart from that famous 6-city study. I forget what the names of the cities were. I think it might have been Pittsburgh, Washington, some other cities. So those are the 6 cities there, and this was the correlation between the fine particles in the air and the rate of death from certain health impacts in those cities. And this is a very strong correlation coefficient, implying that it was in fact these fine particles that were causing deaths. So the particulate is mainly a problem with our diesel engines. And what can we do about particulate? Well, the first thing you can do is put a filter on there. And this is a log scale here. So this is showing with a fine mesh particulate, we can reduce the soot emissions by about 3.5 orders of magnitude. That's quite incredible. They're expensive for the manufacturers to add. That it's comparable with the SCR, but this is a important thing to reduce particulate as well as the unburned hydrocarbons and NOx. The thing with diesel engines, though, we have to pay attention to is a lot of the diesel engines operating in the world are not vehicles on the roadway. And all of the regulations were written for consumer vehicles and driving on highways. So a lot of rail cars, all of your tractors, construction equipment, and just general off-road vehicles in terms of diesel engines are about the same number of engines in terms of aggregate power as you would for what's driving on the road. And so how do we regulate these off-road vehicles? We are introducing regulations in specific industries bit by bit. The real challenge here is where most cars and trucks are generally all engines of the same size, somewhere between 100 and 500 horsepower. Once you get out of that standard vehicle range, you have very small engines running a cement mixer on a construction site to very large 1,000 horsepower engines running trains. The other thing that's different with these engines that aren't used for typical vehicles is they don't change over every 10 years the way you buy a new car or truck. Once you invest in a tractor, you're expecting to use that for a long time. Once you invest in a bus or a locomotive, that's a 30-year product. So the turnover rate is smaller. The rate of penetration of these new technologies, filters and catalytic reduction, they're not solving the problem quick enough, but they do work. So it's just going to take a longer time to get these particulates down. But there has been examples of success. Switzerland was one of the first to really push the filters aggressively and mandate them.
and if they began taking measurements in tunnels through the Swiss Alps as to what the background particulate was. And initially, when they started in 1998, it was 760 micrograms per cubic meter, and they've now reduced that significantly to the order of about 50. So more than tenfold reduction in the particulate in a decade or less. Well, that wraps this emissions up, and that does conclude this section of the course. We'll take an exam on everything to do with combustion, equilibrium, and pollutants, and then we'll move back into the design of engines and valves in the final section.